This problem is a beam under the axial loading of two forces, and they being arranged to exercise the eccentric loading problems. And here the 25 millimeter and B is parameters, and here we're going to exercise here asking is 0, 15, and 25. In the following demonstrations, I'm going to demonstrate part A only, and for the process, and the B and C would have a similar process, and I will provide the solution to all of them to you. So for these problems, if we look at from the front view, and here we place the origin of the corner systems on the neutral axis. And for this loading, here 10 and 10 kilonewtons, and location B and 25 as given. Step 1 is to displace the forces, which is reactions, on any cross-section containing the point of interest. Here is A. For this problem, we're looking for the stresses at point A. Step 2, we calculate the neutral axis on the cross-section. For this example, the cross-section is looked at from this view, and which appear to be rectangles. Again, here is corner systems XY. Looking on the cross-section, these are Y and Z. The neutral axis calculated per the equations like this. And now we look at the first case when B equal to 0. So that is the loading like this. And so we have to express these problems in terms of the loading type we know. And here we equivalent this condition into this, which means we get into the loading which only have the one concentrated loading applied through the centroid or the neutral axis, plus any needed bending that is induced from shifting of the load. And for this case, the bending is induced by shifting this load to this position. So we have to multiply the load by the distance 25. Okay, now this is the what we call the combined loading problems. For this beam, on this section is under axial loading and pure bending. So we use superposition principle. We decompose the loading condition into the axial loading and pure bending. So this is a topic of chapter 2. This is a topic of chapter 4. We apply the equations individually. And for this case, the normal stress on this cross-section, including point A, is calculated by dividing force by area. And for the pure bending, we simply apply the equation minus my over I. And for this case, we already identify on the top portion will be in compression, and magnitude is my over I. Y is the distance measured from the neutral axis to where we're interested, and that given is 0.03 meters, and that's I. So we calculate it from here, that's a 10, the compression, and then we simply superpose the result. So this number plus this number, but also considering the attribute tension, compression. So here we use positive for tension, minus for compression. We got a result. So for this case, at point A, for this original problems, point A is under the compression by that magnitude. And for part B and part C have the similar process. And please refer to the solution in the next page.